Hi everyone, and welcome to the channel. So a family member asked if I could repair this neon sign transformer. Now I use the term transformer to mean this entire assembly, although there's more going on here than just a transformer. In fact, there's two transformers plus this control board, so I suppose you could call this a neon sign power supply as well, but generally these are known as a transformer. And of course this cover right here just fits on the top like so. Now what he said the problem is that when you turn the sign on, so there's a pull chain switch and the sign illuminates the way that it's supposed to, but then part of the sign is supposed to flash on and off, and that section of the sign turns off and then never does cycle back on again. So there's nothing wrong with these transformers. They are putting out the right voltage because the sign is able to illuminate, and there's nothing wrong with the neon tubes because again they do glow correctly. So the problem must be over here in this control board. Now taking a look at this entire transformer assembly, you can see these are very large high voltage transformers, so a lot of iron in the core, and these are 60 hertz transformers. Later types of neon sign transformers used a switch mode power supply, so the transformer would be very small, and if they had a sequencing or a flashing function, a lot of times that was built in right on that board as well. So the whole thing would be a lot smaller. So this is an old style traditional 60 hertz transformers. So the secondary on one of these transformers is 3000 volts and the other one is 5000 volts. So definitely a very, very dangerous voltage. If you're following along and working on a neon sign transformer, you're absolutely doing so at your own risk. Take care and be safe. You do not want to come in contact with the high voltage that's coming out of one of these transformers. Very, very dangerous, absolutely lethal at those levels. Now on this control board, there's another problem over here that you have to be careful of when troubleshooting. Nothing is electrically isolated on that board. So there's some circuitry in here that operates at a much lower voltage than the AC line, and there's some components in here that step that voltage down, or drop the voltage would probably be a better way to say it, because it's not being stepped down like through a transformer. So nothing on this board is isolated from the AC line, meaning that if you have to use an oscilloscope to do any testing over here, or any piece of test equipment that has an earth-ground connection, that would be a big problem to connect to this board, especially if it's just powered right off the AC line. That would be a complete disaster. So it's very important that this be powered on an isolation transformer when it's being tested, because again, there's no isolation on this board. So what I'm going to do is remove this circuit board from this assembly, and then we'll start the troubleshooting and taking a closer look. I don't want to power up this board with it connected to these transformers, because I certainly don't want the high voltage on these leads just flapping around here in the breeze. That's just a disaster. You can't do that. So what I'm going to do is, in place of these transformers, I'm going to connect a small incandescent lamp, and we'll be able to visually see then what's going on. One of them should remain illuminated all the time, and the other one, if it was working correctly, should flash, and based on what I'm being told about this, we're going to see it turn on and then just turn off and not flash at all. So then again, once all that's connected, we can start the troubleshooting on this circuit board. So let me make a few notes about where the wires connect on this board, make the test setup, and let's check things out. Alright, so I had the circuit board removed and I noticed something right away. So take a look at this. So this terminal marked T2, look how loose that is. Well, that's not good. Now of course that means that the solder connections are broken on the back side of the board. So that's an easy fix, and I'll get those touched up. But it's possible that those solder connections broke when I was removing the wiring off of these terminals. Some of the connectors were quite tight, had to work them back and forth quite a bit. They were, took quite a bit of force. So it's possible that those solder connections broke right when I was removing these wires. And based on how the problem was described to me, I don't think this would be the problem anyways. If anything, this would be an intermittent connection. But I spent some time going through the wiring connections on this board, and I have an understanding now how this works. So the AC line is brought in on T3 and on T4. I'll just double check my notes. Yes, T3 and T4. And on T5 and T7 is the power switch. So when the switch is closed, you have a connection between these 2 points. So you can see on the other side of the board, the traces are open right there. So that switch is closing the connection across there. So if we follow the AC line, you're coming in on T4, goes through the switch, comes over here to T6. T6 goes off to the white wire on the transformer, so that's going to both transformers' primaries. And then there's also a path that goes over to these 2 capacitors, and you can see that right there. So the job of these 2 capacitors is to drop the AC line voltage down, and then you can see it comes over here. There's a trace that comes over to those 2 diodes, so that's rectifying that lower AC voltage down to a DC voltage, some filtering with this electrolytic capacitor. And I believe this is a voltage regulator. It's marked as U2. So typically when you see the letter U, that means an integrated circuit. If it was a transistor, it would be marked with a Q. And then there's an integrated circuit right here marked as U1, and this is a 555 timer, super common part. So this is creating the timing pulses that cause part of the sign to flash. Now this integrated circuit needs between about 4.5 and 15 volts to operate. So we'll definitely want to check that voltage first to make sure that it's correct. Now remember, I said that there was no isolation on this board, and you can see that how the connection is made right from the AC line through these components and around. So there's no isolation with a transformer on this board for this low voltage power supply. So when you're probing around here, even though this is a lower voltage and it's rectified into DC and so forth, you have to be very careful that you don't cause a short to ground, because again, there's no isolation from the AC line. So you definitely want to use an isolation transformer for testing. That would help prevent that short circuit to ground problem. But you also have to be very careful about using something like an oscilloscope that has a grounded chassis. You should, for safety, use something like a fluke scope meter that has an isolated ground. Basically, it's floating. All right, so then going back to the circuit over here, this integrated circuit is creating the pulses that are driving what I believe is a triac over here. So a triac is two SCRs back to back. You can think of this as basically a switch that's opening and closing. Now, this terminal right here that's marked as T1 has one of the transformer's primaries connected to it. So if we go back over here, the path is going from T6 through the winding on the transformer, comes over here to T1. T1 connects right to this triac, and you can see that on the back side of the board, right there, that center terminal. When the triac closes, it closes to this side over here, which comes down to this very wide trace right there, and comes over to this much bigger trace over here as well. So again, this is acting like a closed switch, so then that transformer would turn on. And then over here, look at my notes again, yes, T3 is returning back to the AC neutral, all right? Now this terminal right here is going off to the transformer, and it was on, let's see, that's T2, and T2 is the red wire on the transformer. So that's the part of that transformer is running the part of the sign that stays on all the time, okay, because this is just right off of this direct connection on the AC line. So the path on that is going from T6 through the winding on the transformer over to this T2, and then that's returning back to the AC neutral. So that's the general idea of how this board is functioning. So I'll get things set up with my test setup, and I'll make or fix those solder connections, get that taken care of. But then let's power this up and see if it functions as it was described, with the part of the circuit that's supposed to flash not really doing its job. Because again, I don't think this broken solder was, that's probably just happened. I don't think that was really the issue that was going on initially. But we'll find out. We'll get everything powered up here and let's see what happens. All right, so I have the circuit board connected based on how I just explained that it works. And for clarity, I have the test lead colors, so the black, the red, and the white, the same colors as used on the transformer primary wires. And these two incandescent lamps are just taking the place of the primary windings in the transformer. So this circuit is the circuit that should be flashing, and this is the circuit that should remain continuously on. And this yellow test lead is just taking the place of the pull chain power switch, so it's just jumping between those two terminals on the board. And this AC line coming in is off of my isolation transformer and variac. The variac is set to 120 volts because that's the voltage that this works on. And I also have a series connected incandescent lamp on this AC line. It's a 150 watt incandescent lamp. And the purpose of that lamp is to protect from extreme current flowing if there's a problem that occurs. So let's say something happens and the black and white wires touch together, maybe something slips in here or comes out of place, and it causes a short circuit. Instead of having all kinds of problems and sparks and maybe something melts down, all that would happen is that incandescent lamp would glow very brightly. So it's also known as a dim bulb tester. It's always a good idea to have that incandescent lamp for the current limiting when you're working on a test setup like this. Now, quite a while back, I made a video about an isolation transformer, the variac, and a dim bulb test setup. So if you're interested in setting up something like that on your own workbench, definitely check out that video. I go through all the different combinations of how you can set up the variac and the isolation transformer and the incandescent lamp, pros and cons of each setup, and I even show what I have on my own workbench. So definitely check out that video if you're interested in a setup like that. Also, please remember that the voltage that's across this AC line coming in, even though it's off the isolation transformer, it's still lethal. You would get a very serious, if not lethal, shock across this AC line. The purpose of the isolation transformer is to protect from shock from the AC line to ground, because there is no earth-ground reference on the secondary of that isolation transformer. And again, right here, this ground wire is not connected. This is a 3-wire cord, but on the isolation transformer, there is no ground, and the ground connection in the outlet doesn't go anywhere, so this ground connection is just left disconnected. Okay, so let me switch on the variac here, and let's see what happens. So that lamp's on, nothing happened over there. Let's try that again. No, we did get a flash over there, and then that's on continuously. So that's how it was described, that this would flash momentarily and go out, and then that lamp would remain continuously on, or that circuit. So again, these are just simulating the primaries on the transformers. So if this was in the neon sign, this section of the sign would be on continuously. This would be completely off right now. Turn that back off. Let's try that again. Nope, there it came on. Definitely on a longer period of time now. A lot longer. Maybe it's stuck on. Give it a little bit of time here. Oh, there it went off. So, interesting. So I'm not sure, the owner of that neon sign, from my understanding, this would flash rather quickly. I'm not sure if sometimes it was staying on longer or not. Let's give it a little bit of time here and see if anything changes. So it seems to be staying off now. Oh, there it came back on again. Interesting. So maybe this circuit and the 555 timer is perhaps basically pulsing, or causing some pulses in that circuit, just extremely slow. Let's see if it goes back off again. It does go back off. So yeah, it seems like the 555 timer is probably working, but perhaps a capacitor or a resistor has failed or drifted in value, and it's changing the timing cycle on that integrated circuit. Because this is really flashing far too slow, because this is a neon sign. You would want that maybe going like on and then off, and maybe back on again, perhaps off, something like that. Because when this is off, that whole section of the sign is dark, and it seems like it's staying off way too long. So yeah, it just seems like it's slowed way down from what it probably should have been. It doesn't seem like it's working quite right. So let me grab my digital multimeter and let's start taking some measurements, and let's track down the problem. All right, let's take a look at the supply voltage on the 555 timer. So pin 1 is negative, pin 8 is positive. So carefully go in here. Oh, looks good, 9.6 volts. Very steady. So voltage looks fine. Let's go to AC volts and check for any excessive ripple. That's very low, 2.6 millivolts AC, so no problems there. So the supply looks like it's perfectly fine. So I'm inclined to say that that orange-colored electrolytic capacitor is probably working, but we'll check it anyways. There's another electrolytic we can test as well. But it doesn't look like a supply voltage issue. Now the frequency or the repetition rate on that 555 timer is not affected by the supply voltage if it's within the normal operating range. So whatever the value that it's supposed to be flashing at, whatever that repetition rate, if the supply voltage varies, it won't affect the rate. So the rate is set by some capacitors and resistors that are around that integrated circuit. So let's check those electrolytics next. Alright, so let's check the electrolytic capacitors. Turn that on. So we'll start with this orange colored electrolytic. It's marked 330 microfarad, 16 volt. This is 304.2 microfarad, 0.6 ohms ESR. So of course this does not do a leakage test, but the capacitor does appear to be okay otherwise. Usually if the ESR is measuring within a range like this, that looks perfectly fine. It means the capacitor is doing okay. And if you take a look here, the other one is 100 microfarad, 25 volt. That one is right across here, I think, on the board. Yeah, it's these two right here. Oops. Try again. No problems there. 99.28, almost spot on. 0.87 ESR, again, looks perfectly fine. So I don't see any issues with those two capacitors. There's a tantalum right here. Can't really see what it's rated. It looks like plus 15 is a marking, so probably 15 volt rating. But I don't see a capacitance value on it. Let's check it from the top side here. Let's see what this measures. Basically 12 microfarad, probably about right. I need to desolder it to actually know what the value is because I can't see the marking on this capacitor right. Get that touched up there. Right there, I can't tell. And this capacitor is far too small in value to be measured by this tester. So I have an LCR meter I could use to check that capacitor. So I'll go through and I'll check these other resistors, see if they look to be within spec. If everything checks out okay on the board, I'm wondering if this is actually the speed that the board was supposed to run at. And I could check with the owner of the sign, and if he wants to modify it, we could speed this up a little bit by changing appropriate values of components and make that chip cycle a little bit faster. Maybe it was supposed to run this speed, I'm not really sure, but let's continue testing other components here and see how the rest of the resistors look in this other small capacitor. So I have the LCR meter connected to that very small capacitor, and it's measuring as 10 nanofarad. That's exactly what this capacitor is marked, so it checks out perfectly fine. And there are several other capacitors on the circuit board. We don't need to worry about those right now. They have nothing to do with the timing circuit. So for example, there's this brownish colored capacitor right here, and that's part of the triac switching circuit. It has nothing to do with the timing, and we know the triac switches correctly, so there's no problems with that capacitor, that part of the circuit. And then these two blue colored capacitors right here are in parallel. I already mentioned those are for voltage dropping on the AC line, part of the power supply. We know the power supply voltage looks okay, so those capacitors must be working fine, so we don't need to worry about those right now. Alright, so I went through and I checked all the resistors, and I'm not seeing any problems. So I'll go through and I'll show you those measurements. You can see the results on the digital multimeter. Now I had to remove this 100 microfarad electrolytic capacitor. I already checked that earlier in the video. It works perfectly fine. It goes right there on the board. But the reason I had to remove that capacitor is because it was influencing the readings that I was trying to make in this part of the circuit, and it was just skewing the results too far off to make any meaningful measurements. So with that capacitor removed, then the resistance values settled right in. So the reason is there's some current that has to flow out of the test leads. Basically this is like a small power supply when it's being used in the resistance mode, and that voltage that's coming out of the test leads causes a current to flow, and it goes into the capacitor, charges the capacitor up, and you start getting fluctuating measurements, and the resistance value is drifting all over the place as the capacitor tries to charge up. And you'll still see that effect with some remaining capacitors over here as well, but not quite to the extent that this capacitor was causing. Alright, so let me bring the board a little bit closer here, and you can see I'll just start measuring resistors on this end of the board, work across. Now the resistors down here are part of the power supply section, and again some of them are being influenced by components in the circuit, but I can see how they're connected in the circuit, and even though the reading on the resistor might not be exactly how it's marked, it's still very reasonable, so I don't see any problems going on. And same over here. The resistors on the end over here are part of the drive circuit into this triac, and I get, there's some components in parallel with these resistors. It's changing the value some, but again, not a problem because I can see how it's connected in this circuit. Let's get that touched up there, and let's take some measurements. Start over here on R1. So R1 is supposed to be 100 ohms, and yes it is, very close. So R2 is supposed to be 2.5 k ohms. And yes, you can see it's increasing, so there's some capacitance in that circuit, but very close to that 2.5 k ohm value, so no problems there. Again, that's in the power supply section, and that worked fine anyways. So this is R3, supposed to be 7.2 k ohms. Again, looks like some capacitance. And that's connected over by that voltage regulator. It's being influenced by some other components, so the value is down some, but no indication of a problem. I can see how it's connected in the circuit. So unless you remove that resistor, it's just being influenced a little bit by some surrounding components, but it doesn't look like there's any problem. Again, the power supply voltage looked perfectly fine anyways. So R4 is supposed to be 374 k ohms. That's spot on, no problems there. Looks very good. So R5 is supposed to be 680 ohms. Connection there. Very close to that value, no problem. So R6 is supposed to be a 1 k ohm. You can see it's under half the expected value. But that's not a problem because there's some other components in parallel with that 1 k ohm resistor. It's basically pulling that value down. And that's also in that triac drive, and that's working perfectly fine anyways, so there's no problem with that resistor. And on R7, it's supposed to be 150 ohms. Get a connection here. There it is. Very close. So no problem. So all the resistors look perfectly fine. I'm not seeing any issues going on. Now, there's two resistance values that we need to measure right on this 555 timer. And those two resistance values, plus the value of this capacitor, will tell us basically the frequency and the on-off times, which you can also figure out then the duty cycle, of what this circuit should be running at. So let's make those measurements, then we'll go over to the data sheet. We'll take the values that we measure, put them in on the data sheet, and let's make a decision. Is this circuit working correctly with the measured values? And I went back in the video and I timed how long we were seeing those incandescent lamps turn on and off. And they were turning on and off basically at a 50% duty cycle, which is good. And they were turning on and off at about 28 seconds to about 30 seconds on, about 28 to 30 seconds off. So if the values that we put in mathematically from what we measure here, put those values into the formulas, if it returns the results and it says that yes, that's the speed that this should be running at, then it means that this circuit is working perfectly fine. And really we just need to modify it to change the speed. Now I talked to the owner of the neon sign, and he wasn't expecting this to run with a 30-second on, 30-second off. And he said that he would actually prefer it to be about 10 seconds on and 10 seconds off. Now you can modify the speed that this would run at by changing just this capacitor. And that can also be figured out mathematically, so we don't need to do trial and error with different capacitors. We can figure out which value it should be. Now we don't want to touch the resistors, because if you mess with the resistors, that would change the duty cycle. And we don't want to affect the duty cycle, because with the neon sign, it should turn on and off equal durations. So you wouldn't want the sign to be, off, off, off for a long time, and then on, off, and then off, off, off for a long time. That wouldn't work right. And also you wouldn't want the sign to be on for a very long time and then off and then right back on again. Obviously duty cycles like 10% or 90% aren't appropriate for this kind of application, but 50% duty cycle is perfect. So we don't want to mess with the resistance values, only this capacitor, and the capacitor will change the time, but not the duty cycle. So we'll take a look at the data sheet, and I think this will all make sense when we start looking at the formula and how it all figures out. But the two measurements on here that are very important to make are, let's see here, from 2 to 7. So let me show you on the integrated circuit. If you're not familiar with on integrated circuits, see that little dot right there? So that's by pin 1. So you count pin 1 down to 4, then over to 5 and up to 8. And that's the pin sequencing. So if I get that touched up there, okay. So let's go from pin 2 to 7. So there's 2 and 7 right there. So 448 k ohm, 449, maybe a little bit of capacitance in that circuit. Let's call it 450 k ohm, let's round that off. It's very close to that value, so we'll say 450 k ohms. And then between pins 7 and 4, so here's 7, here's 4. So that's, let's call that 1.16, rounded off to 1.161 k ohms. Very close to that value. Also, if I reverse the polarity, I think it does have an effect, at least on one of these measurements. That's, yeah, 1.161, very close there, so that's fine. Go back to the other measurement here, 2 to 7 with the different polarity. Yeah, it is a lot lower in that direction. We want to use the higher resistance value. That's lower because something is conducting with that polarity. Okay, so we'll go with 450 k ohms and 1.161 k ohm and 100 microfarad. Let's put those numbers into the formulas and see what it tells us about how this circuit should be functioning. If it comes up with some values that don't match what we saw with the about 30 seconds on and off, then we need to go back to troubleshooting and figure out what's going on. But if it matches with what we actually saw working, then let's just modify this, and it'll be working very well then. So again, the owner of the neon sign, when he plugged the sign in, he wasn't expecting this to cycle so slowly, and he told me that he plugged the sign in, he didn't get the flashing effect that he thought it was going to do. He unplugged the sign, tried it again, it didn't work right, unplugged it, thought there was something wrong, didn't try it again. And obviously when we tested it here and I gave it some more time, then suddenly we noticed that it was starting to cycle, but very, very slowly. And he was basing his decision on how fast it should cycle or what he thought it was going to do based on some other neon signs that he has that sequence on and off much faster. Let's look at the datasheet for the 555 timer. So this datasheet is from Texas Instruments, and that's the manufacturer of the integrated circuit on the board that I'm working on. Now the 555 timer on the board is marked as TLC 555, and that's this very low-powered version from Texas Instruments. So right here it mentions that functionally it's interchangeable with the NE555, has the same pinout, so that's the original version. This is a single supply operation, but it goes from 2 volts to 15 volts, so I think the lower end of that voltage range is a little lower than the original version operated on. And it makes sense that they used a low-powered version on this board because of the type of power supply that's being used is a very low current type of supply. So if you want to pause the video, you can read about the general description on this page. Move this down just a little bit here, you can see the rest of it. Simplified diagram, what's inside the chip. There's a lot of information already published about the 555 timer. It's extremely popular and it's been around for years. There's a lot of resources out there online and also books that have been written. So I'm not going to go into a lot of theory of operation here. We'll just concentrate on what's needed to get this board up and running. Alright, so let's take a look at this other page right here. So up at the top on this page you can see, make sure that's touched up there. So astable operation, that's how it's being used. It means it's acting as an oscillator, it's re-triggering over and over again. And then if I move the page down, you can see there's some other formulas down here. We're just interested in these two formulas. We'll take a look at those. Pause the video if you want to read the rest of that. Right here it does mention that these formulas are valid for frequencies below 100 kilohertz. Well, we're way below that. We're down in the millihertz range. This chip can work up to several megahertz, so at higher frequencies some other things need to be taken into account. But just moving this back over here, that over, and put my calculator here so you can see that. And make sure that's in focus there for you. So this is the general setup for the 555 timer in the astable operation. This is how it's being used on the board. And here are the values of the components. So these are the critical values for the timing and the frequency that it creates in the duty cycle. So we already measured those values. That's the 100 microfarad capacitor that I removed when I was taking some of the resistance measurements. So if we look at these two formulas right here, this tells us the time high and the time low, so TH and TL. So right here, the 0.693 value that you see in both of those formulas is actually the natural log of 2. So on my calculator here, if you just go natural log 2, you can see 0.693 and a long decimal number, and they've just rounded it off there. So that's where that value comes from. So let's take a look right here. It says 0.693 and then multiplied by, in parentheses, RA plus RB, so that's RA and RB, close parentheses, and then multiplied by C, which is this capacitor. So capacitance is in farads, so 100 microfarad, you need to move the decimal point over, and resistance is in ohms, again you have to move the decimal point over. So let's enter this in, see what we get. So 0.693, parentheses, RA is 1161 plus RB 450,000, close parentheses, multiplied by capacitance 100 microfarad, so 0.0001. That's the time high. So it's telling you right there, make sure you can see that. So 31 seconds, and obviously some change, but just call it 31. So I'm going to just make a note here that comes up to 31 TH. Okay, so that's good news because that basically fits with how the circuit was operating. We were seeing that it was on for about 30 seconds. When I went back and checked the video and I ran a timer, and I just watched the video and I timed how long the lamps were cycling, and they were on for very close to 30 seconds. So that's actually good news to see that. Looks like that's probably how they designed the circuit. So we'll just have to modify it to make it run a little bit faster. But let's look at time low. So we have 0.693, and then we're going to multiply that by RB, which is the 450,000. Capacitance multiplied by that, so 0.0001. 31, look at that, 31 and some change. Oh, definitely a 50% duty cycle, so no problems there. So that's exactly how we were seeing this operate. It was on for about 30 seconds, off for about 30 seconds. So it tells me that this circuit board right here is definitely working correctly. There's nothing actually wrong with it. There are no failed components on this board. So we just need to modify the value of this capacitor so that it causes this to run a little bit quicker. And again, the owner of the sign set about 10 seconds on and off would be ideal. So let me go back over here. We know that this is a 50% duty cycle, so we can use this formula here. It's a little bit shorter. We'll just start with this one here. So if we go 0.693, multiply that, we don't need parentheses here, we just multiply by RB, which is 450,000, multiply that by capacitance. Let's say we go with 10 microfarads. So we have to use values that would be standard. So let's try to lower this way down from 100 microfarads to 10 microfarads. So go here, 0.00001. Well, it obviously has a change, but look at that. It would be too fast. So it's about 3 seconds. So we don't need to go into the other formula here. It's going to calculate the same way. We know that this is a 50% duty cycle. So yeah, that's too quick. Let's go to try what would be another standard value, 27 microfarad, 33, try 33 microfarad. I think that might be, let's try that. I'm thinking of something that's maybe not quite halfway in the range. Obviously, 50, 60, somewhere right there would be kind of halfway, but we want to slow it down a considerable amount from 30 seconds or so. So let's try 33 microfarad. So 0.693 times RB 450 000 times 0.00003. Look at that. Perfect. How cool is that? 10 seconds. Spot on. Now there's going to be some variation in tolerance and components, so if you time it out, it's not going to time exactly to that, value, but it's going to be very, very close. So I think 33 microfarad is the magic number. That's what we need to use for this capacitor. So hopefully I have that in the parts bin. It's a standard value. So let's just run it through on the other formula. It should work out the same way. So if we go 0.693 parentheses resistance of A 1161, add that to 450 000, close parentheses, multiply that by our new value 0.00033. There it is. 10 seconds. Outstanding. 50% duty cycle, 10 seconds on, and 10 seconds off. So, yep, that's what we need to do. So let me get a 33 microfarad capacitor, put it onto that circuit board, get the test setup hooked up, and let's see if the results match what the calculations show. The 33 microfarad capacitor is installed. So you can see it on the board right here. So the markings are right on the side, right there. So 33 microfarad, 50 volt. Now when you're replacing electrolytic capacitors, you always want to watch the polarity. So you can see the board has a positive mark right there, and the capacitor has a negative mark on the side. But it wasn't obvious that the board was actually marked because the old capacitor was larger in diameter. It filled this entire circle, so it was covering that positive mark, just like this capacitor is covering the polarity mark over here. So it's not obvious that the board is marked. So before I removed the old capacitor, I just made a note which side was negative, so that when I removed the capacitor, if come to find out there was no polarity mark on the board, it would be obvious, which way to install the new capacitor. It saves a lot of headache later on. So some boards are not well marked, so don't always assume that you'll find a mark under the capacitor. Also, when you're replacing capacitors in general, you always want to use an equal or higher voltage rating than the original. So the original capacitor was 25 volt. This is a 50 volt capacitor, so well above the required voltage that's in this circuit, plenty of safety margin. But you'd never want to use a lower voltage rating than the original capacitor. Now, of course, within reason, this is 50 volts, perfectly fine. Obviously, the capacitor physically fits on the board. It's even smaller than the original. But you're not going to be using something like a 250 volt capacitor because it's just going to be physically too large. It's not going to fit on the board. All right, and then these are the capacitors I had on hand already. So this is what I used. So from Mauser Electronics and Panasonic brand, very high quality. All right, let me get this circuit board connected into the test setup, and let's see how it performs. Okay, the test setup is complete. Looks like everything is in place here. Nothing's touching that shouldn't be touching. Everything looks good on the test clips. Alright, so again, this is on the isolation transformer and the variac. The variac is preset to 120 volts. Of course, it's not on at the moment. So I will switch it on right now. And that incandescent lamp for safety is in circuit as well. It's in series. I talked about that earlier in the video. Okay, here we go. So it's normal that lamp comes on and just stays on, as we saw before. Let's see if this one starts cycling with 10 seconds on and 10 seconds off. Okay, there it's on. So that seems like that was probably a shorter duration than before, so that's good. yeah, that seems to be cycling faster. Let me grab my cell phone, the stopwatch feature here, and let's time this, see how accurate this is. So what I'll do is I'm just going to set this, or hold this over here, like that. So you can see the lamps over there. So I'll wait till that comes back on, and then we'll time it when the lamp starts on again. Okay, there it goes. Very close. Look at that, 9 seconds. Cool. Let's try the off cycle. So it has to turn back on. Now when it turns off, I'll time it again. Nine seconds. Perfect. Awesome. So it looks like this is working very close to the 10-second interval. So I think the owner of this neon sign will be very happy with this result. It's going to work the way that he wants, and it won't be off so long and then on so long with that 30-second interval that it was originally set for. So excellent. The capacitor is doing what it's supposed to, and it changed the cycle to the faster repetition. So everything worked out, and it looks like the circuit is working the way it's supposed to. Very happy with the result. Alright, the circuit board's back in place. All the wires are connected. I'll get that top cover put back on the transformer, and then this transformer can be reinstalled on the neon sign. Should be good to go for many more years. So if you enjoyed this video, you can let me know by giving it a thumbs up. And if you're enjoying the content on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. Lots of projects in the queue. You won't want to miss any of those. And don't forget to tap the bell symbol to be notified when I do post a new video. As always, thank you for taking time to watch. And until next time, take care. Goodbye for now.